guys. Good afternoon. Can you just give me an indication if you can hear me now? Those of you that are currently watching on YouTube, Teams is buffering for some reason, but it's connecting now. If you can hear me, then cool. I'm about to open up the Teams link now. Can someone just type in the comments whether you can hear me or not? Teams is just giving some problems right now. Okay, I will be continuing. While I'm waiting for Teams, I'm gonna continue with tutorial number 2, motion in one direction and motion in a plane. Okay, that is for tutorial number 2. And we're going to start with question. Let me just go to it. Is it there? It is. I go to this particular question. And it seems like I'm going to have to actually show you the graph that I'm talking about, that I'm going to be using in this problem. Okay, I think I might have to find the actual problem because they don't provide the graph that you're going to need here. Okay. So let's see. Question 1. It says, okay, let me just share.
Hey guys, so today I'm checking out the station on Greek for the very first time. Fulma app directed me here. The menu is quite, there's quite a couple of things on.
Good afternoon, guys. It seems my teams have finally kicked in. Just by a show of hands, a thumbs up if you can see my screen at the moment. There seems to be some issue with Teams at the moment. Okay. At least one person can see my YouTube. There seems to be some lag. I do not know where it's coming from. And Teams seems to be quiet. Let me put on my mic. Good afternoon, guys. I just switched on my mic. Didn't see it was off. By show of hands, can you hear me and see my screen? Thank you, Rashan and Sam Carlos Sam there on YouTube. Okay, thank you. So, quite a lot of you can see and hear my screens. You can see me sharing. If you want to ask a question on Teams, please just switch on your mic and ask me. I'm open. I've opened the YouTube chat section so I can see that one first, but I will continuously be checking Teams's chat. Okay, now today we're going to be doing motion in one direction and motion in a plane. Okay, so just plain old Newtonian motion. Okay, now the question there that you're seeing there, let me just scroll up. Question 1, it says a position time graph for a particle moving along the x-axis is shown in figure 2.7. Okay, now you don't have that picture. Okay, I'm going to show you. It's in your textbook. Okay, I'm going to get a picture of it now. Let me just open up my textbook here, then I will show you that picture. Let me just get my textbook. It's supposed to be here. Now, while I'm opening my textbook, okay, this is question 1. Okay, while I'm opening my textbook, a position time graph. Can I just ask, if you have a position time graph, what information can you get from a position time graph? Anyone hazard a guess as to what type of information you can get from a position time graph? Anyone? Anyone would like to hazard a guess as to what type of information you can get from a position time graph? I'm just going to show you the figure for this particular problem that we're dealing with. Position time graph, what type of information can you get from it? There seems to be some disparity between. Okay, there it is, figure 2.7. I found it. I'm going to show it on my screen now. Okay. Okay, so we have a position time graph. First, they want us to find number one, the velocity, the average velocity from t equals 1.5 seconds to t equals 4 seconds. So they want to find the average velocity between these two time intervals. Okay, find the average velocity in the time interval t equals 1.5 seconds to t equals 4 seconds. Okay, so find the average velocity. Okay, let me just show you the graph. There's the graph. Okay, I'm showing you the graph. Now, let's see. Okay, we have t 1.5 seconds and t equals to 4 seconds. Okay, now they're asking us to find the average velocity. First of all, you need to know how to calculate average velocity. Average velocity is equal to the position at some point x2 minus the position at another point x1 and the time at position 2 minus the time at position 1. That is average velocity. Okay, now we know that at t equals to 1.5 seconds, the position is, according to this position time graph, at t equals 1.5 seconds. If we move up, we see that the position is at 8 meters. So at t equals 1.5 seconds, x1 is equal to 8 meters. Okay, now at t equals to 4 seconds, let's go here, 4, the position is 2 meters. Okay, so x2 is equal to 2 meters. Okay, so there we have all the information required to, let me just move here, to calculate the average velocity. Okay, now if we continue and substitute all these values that we have that x2 is 2 meters minus x1, which is 8 meters over t2, which is 1 point t2, sorry, and that's t1, t2, which is 4 seconds, minus t1, which is 1.5 seconds, 1.50 seconds. Okay, and if you work that out, you get that it's minus 6 over 2.5, which is negative 2.4 meters per second. So the average velocity is negative 2.4 meters per second. Okay, is there any questions? The average velocity is negative 2.4 meters per second. Okay, there seems to be no questions. I'm going to continue with the second part of that question. Let me just flip back to the question. The second part of the question is determine instantaneous velocity. So the instantaneous velocity. Okay. Determine, that's question 1. This is part 2 of question 1. Determine the instantaneous velocity. Okay, now for instantaneous velocity, you need to know the slope at that exact point, the slope of the tangent that cuts the graph at that point. Okay, so you need to know the slope. So determine the instantaneous velocity at t equals 2 seconds. The instantaneous velocity, at t equals 2 seconds. Okay, so the instantaneous velocity at t equals 2 seconds. So we need to determine the instantaneous velocity at t equals 2 seconds. Can you guys on Teams still hear me? By a show of hands, can you still hear me? You need to determine the instantaneous velocity. Going ahead, calculating instantaneous velocity. Can you guys still hear me on Teams and in YouTube? Okay, there seems to be a bit of a lag, but it seems you can still hear me. Okay, now continuing, we need to calculate the instantaneous velocity at t equals 2 seconds. Okay, now let me show the graph again. Okay. So at t equals 2 seconds, right where the straight line cuts the graph, okay, that's where we need to calculate the instantaneous velocity. Now, here's the thing, okay, if we find the gradient of that slope, the slope of that line, that green line, we will have the instantaneous velocity right at that point where it touches the graph at 2 seconds. Okay, meaning if we find gradient of this line touching the graph at 2 seconds, we find the instantaneous velocity at 2 seconds. Okay, so let's see. Okay. Let's try to find the slope of this green line. Okay, so at P1, let's pick, you can pick any two positions. I'm going to pick, let's say at 1 second, I'm going to take it at 1 second. At 1 second, its position is approximately 9.5. Okay, at 1 second, its position, so T1 at T equals to 1 second, the position X is X1 approximately 9.5 meters. Okay, if you look at the graph, okay, at 1 second it's approximately 9.5. Okay, remember we're trying to find the slope of the green line because it touches exactly at 2 seconds, and that means that the gradient of this line will give me the instantaneous velocity at 2 seconds. Okay, now we need another point. Let's say at time t2 equals to 3.5 seconds. Okay, let's look at 3.5. We'll write here 3.5, it is 0. Okay, so at 3.5 seconds, the position x2 is equal to 0.00 meters. Okay. So now we have 2 points on this line. Okay, so in order for us to calculate the instantaneous velocity, we just need to find the slope of this green line. So the instantaneous velocity therefore is equal to x2 minus x1 over t2 minus t1. So x2 is equal to 0.00 meters minus x minus 9.50 meters over t2 is 3.5 seconds minus 1 second, and that gives us, if you work it out, negative 3.80 meters per second. Okay, so we find that the instantaneous velocity at 2 seconds is negative 3.8 meters per second. Okay, it is accelerating at 3.8 meters per second in the opposite direction that you have chosen as positive. Okay, now number C, or just C, whatever you choose to call it. Okay, the question at C is, let's go back to the question. It asks, at what value of t is the velocity 0? So at what time is velocity 0? Uh, Somelise, Miss Somelise, you have a question?
Yes, sir. I wanted to ask, why did we use for question number 2 for the instantaneous velocity? Why did we use t like was it 1 second and 3.5 seconds? Why
You
instead of the
just
2?
you can use 2 as well. Remember, you just have to find the slope of this line. Okay, so you can use any 2 points on that line. I chose those 2 arbitrary points. Okay, you could have used 2 if you want. You don't actually need to use 2. Remember, we need to find the the instantaneous velocity at the point 2, right? But this line, this straight line, touches it exactly at 2 seconds. So you can use any 2 points on that straight line to find the instantaneous velocity at that point at 2 seconds.
Okay, sir. Thank you.
Okay. So the last question, question number 3. Why am I saying C? It should be 3, Roman numerals 3. The third question in question number 1, the third part of the question asks the following. At what value of t is the velocity 0? Okay, at what value of t is the velocity 0? Is there anyone that would like to answer? At what value of t is the velocity 0? I'm going to show the graph again. So at what value of t is that velocity going to be 0? Now remember, the slope of this tangent line, if you draw a tangent line to any point on this graph, it's going to give you the instantaneous velocity at that point. Okay, now if you were to draw a slope at any point, if you were to draw a green line at every point of the graph, okay, that point where it touches the graph would give you the instantaneous velocity at exactly that point. But at what point would that velocity be 0? Okay, at what time would that velocity be 0?
So I think it's at 4 seconds.
Yes, that's correct. At approximately at t approximately equal to 4 seconds. Okay, since this is not a very clear graph, we're just going to say it exactly 4 seconds. Oh, we can't say exactly four. Well, you can say it 4 seconds, I would mark it correct, but it's at approximately 4 seconds. Then your slope would have your graph would have its lowest velocity, where the velocity is 0. Okay? Its lowest numerical velocity. Okay, that's question number 1. Are there any questions regarding question number 1? If there are any questions regarding question number 1, especially in question 1 and 2, where we had to calculate average velocity and instantaneous velocity. Average velocity between two set points in time, we're calculating the velocity. The average velocity and instantaneous velocity, we're calculating the velocity at an exact point, meaning we calculate the slope of a tangent line at that point. Okay. Now, going on to question number 2. If there are no questions, I'm just going to search for about 10 seconds and to see if there are any questions. If there are any questions. Any questions at all? Okay. I'm going to continue with question number 2. If there are no questions, please at any point, please just stop me so I can answer any questions that you might have. And if we look here, we got minus 2.4 meters per second as an answer, minus 3.8 meters per second, and then at approximately 4 seconds. Those were our answers. Question number 2. Question number 2. I assume there's no more questions for question number 1. So let's go to question number 2. Okay, the first part of question number 2 says, well, let me read the question first. I'm a bit hasty. First, read the question thoroughly. Question 2 says, a truck covers 40 meters in 8.5 seconds while smoothly slowing down to a final speed of 2.8 meters per second. They're asking us first find its original speed and then to find its acceleration. Okay, so we have a truck. It covers 40 meters in 8.5 seconds, so it's busy decelerating, and in that period of deceleration it covers 8.5 in that period of deceleration a time of 8.5 seconds passes while it's slowing down to a final speed of 2.8 meters per second. So so 1, they're asking us find its original speed. Now, average speed, or let's say average distance covered, average distance covered this is distance x. Average distance covered is equal to average speed multiplied by time. Remember, distance is speed multiplied by time. Okay, so average distance covered is speed multiplied by time. But we also know that average distance, average velocity, I mean, not velocity, it says no direction, so average speed, sorry. Average distance is equal to average speed multiplied by time. But we know that average speed is just equal to the initial speed plus the final speed divided by 2. And that gives you your average speed. And that's multiplied by t, the time it took. Okay, now we want to find the original speed, v initial. Okay, v initial. We know, we divide by 2. We know what the final speed is. It is 2,8 meters per second. I'm not going to insert. We want the initial speed. We know what the final speed is. It's 2,8 meters per second. We know, oh, let me just put in there meters per second. And we have that the time it took for this truck to decelerate is equal to 8.5 seconds. So 8.5 seconds. Okay. Now if you work out, and the average distance covered in that time, the average distance AVG x AVG, the average distance covered in that time is 40 meters. Okay. Now if you solve for the initial velocity from that problem, you solve for an initial velocity, you are left with, or let me just, if you divide by 2 and then take it over, you are left on this side with 2,8 meters per second, v initial plus 2,8 meters per second. And since you are multiplying by 8.5, you divide by 8.5 and then you multiply by 2. Okay, that gives us on this side 9.41 meters per second. Okay. You can work out this math. 8.5 divided by 2 is 4.25. 4.25. 40 divided by 4.25 gives you 9.41 meters per second. Okay. And then if you're adding 2.8 on this side, so if you want to get rid of 2.8, you need to subtract on both sides, giving you that initial velocity is equal to 6.61 meters per second. That is your initial velocity of 6.61 meters per second, your initial velocity. So you have an initial velocity, you worked out the initial velocity, and the next question is find its acceleration. Okay, so find its acceleration. Question number 2, find the truck's acceleration, or more accurately, its deceleration. Acceleration is equal to the final velocity Vf minus V initial over the time it took for that change in velocity to occur. Okay, so acceleration is equal to V final minus V initial over the time it took for that acceleration to occur. Now, the final velocity we've been given to be 2,8 meters per second minus the initial velocity we just worked out as 6.61 meters per second over the time it took for the change in velocity is 8.50 meters per second. Oh, sorry, 8.50 seconds. Seconds are going to cancel, giving you, not cancel, it's going to become second per second squared, giving you 2,8 minus 6.61 is going to give you negative 0,448 meters per second squared. So that gives you your acceleration, or more accurately, your deceleration of this truck in 8.5 seconds. Okay. Are there any questions? Any questions regarding this particular problem? We worked out the initial velocity from an average distance given, and we worked out the acceleration. Are there any questions regarding this particular problem? Any questions? If you have any questions, please raise your hand, or please type it in the comment sections of either Teams or WhatsApp, Teams or your Yaba Physics channel on YouTube. If you have any questions, please ask. Okay. Continuing. I'm going to wait just a few more seconds. Maybe there are some questions being typed. If you have any questions, please feel free to ask. Okay. Question number 3. Wait, any questions? Question number 3. Questions. Okay, let me continue. Question 3. An inquisitive physics student and mountain climber climbs a 50-meter high cliff that overhangs a calm pool of water. Okay, so we have a 50-meter high cliff overhanging a calm pool of water. He throws 2 stones vertically downward, 1 second apart. Okay, and he observes that they cause a single splash, meaning they hit the water together. Okay, so first he throws 1 stone down from a 50-meter height into the pool of water, throws 1 stone down, then a second later he throws the second stone down, but they hit the pool at the same time. Now the first stone has an initial speed of 2 meters per second. Okay, now I like this problem. It's a very interesting problem, projectile mechanics. Okay, so projectile motion. Okay, now here is very, very, very important. Okay, I'm taking upwards as positive. I'm taking upwards as positive. I'm taking upwards as positive. Okay, upwards is positive. So from our equations of motion, we have that the final distance in the y direction, so that's positive y, that's x. So the final distance in the y direction is equal to the initial distance plus the initial velocity in the y direction plus a half times the acceleration in the y direction times the time squared. Okay, you've all seen this formula before. This is not part of the formula. Okay, now let's see what we have. The final distance in the y direction is negative 50 meters. Let's just put down everything we know. It's negative 50 meters. The initial velocity in the y direction is equal to, this is for rock number 1, and that is negative 2 meters per second. It's been given. Remember, we are choosing upwards as positive, so everything going downwards as negative. And our acceleration in the y direction is negative 9,8 meters per second, okay, squared. So there we have everything. So we can find, if we substitute everything, we have that the initial distance in the y direction equal to 0 plus negative 2 times t plus a half times 9,8, negative 9,8. Let me just remove the meter sign there, not necessary at the moment, times t squared. Okay, now that gives you a quadratic formula, okay, in which you need to solve for t. Okay, now if you use the quadratic formula, you have that T is equal to -2. I'm not going to, you've all done this in math. You all know how to use the quadratic formula. This is B2 squared minus 4 times 4.90 times -50. Don't forget all your negatives, over 2 times 4.9. Okay, so that gives you an answer of 3 seconds. Okay, 3 seconds. Okay, so how long after the release of the first stone do the two stones hit the water? Okay, so we just calculated the time it took for the first stone to hit the water, 3 seconds. So the first stone takes 3 seconds to hit the water if it travels a distance of 50 meters and has an initial velocity of 2 meters per second while accelerating at 9.8 meters per second squared. Okay, so we have the time it takes for the first stone to hit the water. Okay? The question number 2 then is, question 2 then asks, what initial velocity must the second stone have if the two stones are to hit the water simultaneously? Okay. Now we know first of all, well, immediately that the second stone takes 3 minus 1 seconds to reach. That is equal to, so 2 seconds. So the second stone takes 2 seconds to reach the pool of water because it is thrown 1 second after the first one, and the first one took 3 seconds. The first stone takes 3 seconds to reach the pool of water, and the second stone was thrown 1 second after that, and they reached the pool of water at the exact same time. So the second stone takes 2 seconds to reach the pool of water. Now, going off the formula that we just used, we know that the distance it travels is equal to the initial distance plus the initial velocity times time plus a half times the gravitational acceleration, or we don't even have to write, times the acceleration times the time squared. That's the acceleration in the y direction initially. Okay, so the distance it travels, if we solve now, we want its initial velocity. We want the initial velocity of the second stone. Now if we solve for v initial, we have the following formula. Okay, we have that the final distance it traveled minus the initial distance it was at, minus a half times the acceleration in the y direction times t squared over the time it took to travel the distance. Okay, plugging in all our known variables, we have that yf, the final distance it travels, is 50 meters minus it was initially at 0 minus a half, that's 9.8, times the time it takes is 2 seconds, that's 2 squared, over 2 seconds. And if we solve for that, punch it in on a calculator, we have that it takes approximately, its initial velocity is approximately 15.3 meters per second. That is the speed at which the second stone has. Its initial velocity is approximately 15.3 meters per second. So the first one has a speed of 2 meters per second, while the second one has a speed of 15.3 meters per second. That is because it needs to travel, the reason is because it needs to travel much faster to reach the water at the same time as the second one, because it has a shorter time it can travel the same distance. So it needs a higher speed. The distance stays the same, but its time is shortened, meaning its speed must increase. And the last question, what is the speed of each stone at the instant that two stones hit the water? So we have the distance for each one, and we have the initial speed for each stone. So we can calculate the speed at which each stone hits the water. Okay? So for the first stone, let's see. For the first stone, V initial, for the first stone, the initial velocity in the y direction is equal, the final velocity in the y direction is equal to the initial velocity of the first stone. This is not an I, this is, sorry, that is the first stone. We do this. The final velocity of the first stone is equal to the initial velocity of the first stone plus its acceleration times the time it took, the time of the first stone times the acceleration of the first stone. Okay, so the initial velocity of the first stone is 2 meters per second plus its acceleration is 9,8, negative 9,8, and the time it took the first stone to reach the bottom was 3 seconds. So it has a final velocity of, if you add negative 2 plus negative 9,8 times 3, that gives you a final velocity of negative 31.4 meters per second. Now if you ask yourself, okay, the first stone had a velocity of negative 31.4 meters per second. Ask yourself now, will the second stone have a higher velocity or a lower final velocity? So the final velocity of the second stone, we work it out. It had an initial velocity plus an acceleration times the time it takes the second stone. Now, the initial velocity of the second stone we worked out as 15,3 meters per second plus its acceleration. It has the same acceleration, 9,8, but it traveled a shorter time, 2 seconds. And if we work it out, we get negative 34.8 meters per second. So the second stone hits the water at a much higher velocity than the first stone, which makes sense. Okay. And that is exactly what the answer said we should have gotten. Okay. Continuing, is there any questions on problem number 3? Are there any questions before we move on to problem number 4? Are there any problems? Any questions? Are there any questions? Any questions? Seems to be no questions. Question number 4 is a very, very interesting problem. I think someone asked me last week how to do calculations using unit vector notation. Question 4. A fish swimming in a horizontal plane has a velocity in the I hat direction, has a velocity v initial which is 4,0 in the I-hat direction plus 1 in the J-hat direction at a point in the ocean where the position relative to a certain rock is 10.0 minus 4, 10.0 in the I-hat direction and minus 4 in the J-hat direction. After the fish swims with constant acceleration for 20 seconds, its velocity is, so it has an initial velocity and it has a final velocity 20.0 I minus 5.0 J meters per second. The question is, what are the components of the acceleration of the fish? So number 4, the components of the acceleration of the fish. Now the acceleration in the I-hat direction is just equal to the change in the velocity in the I-hat direction over the change in time. The change of the velocity in the I-hat direction, okay, the final velocity is 20 meters per second, 20 I-hat minus the initial is 4 I-hat and it takes a time of 20 seconds. So 20 seconds. So we have a final acceleration in the I-hat direction of 0,8 meters per second squared in the I-hat direction. Okay, so there we have our acceleration in the I-hat direction. Now our acceleration in the J-hat direction. Same procedure. Our acceleration in the J-hat direction is the change in the velocity in the J-hat direction over the change in time. The final velocity in the J-hat direction is negative 5.1 J-hat minus the initial velocity in the J-hat direction is 1 in the J-hat direction, and that it took 20 seconds. So we have that the final velocity is negative 0.3 meters per second squared in the J-hat direction. So there we have our two velocities, the components of the acceleration of the fish. So this fish actually has this following acceleration. It has 0.8 meters per second in the I-hat and negative 0.3 meters per second squared in the J-hat direction. That is question number 1. Question number 2. Continue with question number 2. If there are no questions, please just if there are any questions, stop me and ask me. Otherwise, I shall continue. Question number 2 says, what is the direction of its acceleration with respect to unit vector I? Okay. So the direction of the acceleration question number 2, the direction of its acceleration is going to be theta is equal to the tangent inverse of negative 0.3 over 0.800. That's gonna give you an answer of negative 20.6 degrees. So it's negative 20.6 degrees, but we always measure from the positive x angle, so it's going to be 360 degrees minus 20.6 degrees. Therefore, theta is equal to 339 degrees from the positive x-axis. Okay, so from the positive, so there we have ax is equal to 0.8 and ay is equal to 0.3, and it is in the direction 339 degrees. Okay, are there any questions? If there are no questions, I will continue. Are there any questions, or is it clear? Now, the last question asks, if the fish maintains constant acceleration, meaning it travels 0.8 meters per second in the I-hat direction and approximately negative 0.3 meters per second in the y-hat direction, in the j-hat direction, where is it at 25 meters, at 25 seconds? Where will this fish be at 25 seconds, and what direction is it moving? Okay, now you need to know that at at t equals 25 seconds, the fish's position is specified by its coordinates, and the direction of its motion is specified by the direction angle of its velocity. Okay, so its final position in the x-z direction Okay, so its final position. Let me just do this part on a clean page. This is part number 3 of this question. We need to find this fish's final position. Question 4, number 3. If the fish maintains that constant acceleration we just worked out, where is it at 25 seconds and in what direction is it moving? Okay, now its final position in the x direction is equal to its initial position plus its velocity times its initial velocity in the x direction times time plus a half acceleration times time squared. So we will have its final position. It's initially at 10. Let's see. Its initial position is 10 plus 10.0 plus its initial velocity of 4. There we have its initial velocity, 4 times the time of 25 seconds they're asking us, plus a half times the acceleration. In this case we work it out as 0,800, and the time is 25 seconds, and we square it. Okay, that gives us 360 meters is its final position in the x direction, and its final position similarly in the y direction. We're going to work it out similarly. Its initial position in the y direction plus its velocity in the y direction, initial velocity divided times the time, plus a half times the acceleration in the y direction times the time. Okay, now its initial position in the y direction is -4 plus its initial velocity in the y direction is 1, and the time it takes is still 25 seconds, plus a half times its initial acceleration. We worked it out to be -0.3 multiplied by the time it takes is 25 squared. So its final position in the y direction is 72.7 meters. So we have its initial position in the y direction, So you have its final position in the x direction and its final position in the y direction. Now its velocity, its final velocity in the x direction, so its final velocity in the x direction is equal to the initial velocity in the x direction plus the acceleration in the x direction times the time. Its initial velocity in the x direction is 4 meters per second plus its acceleration of 0.8 multiplied by the time of 25 seconds will give you its final velocity of 24 meters per second. So now we have its final position, and we have its final position and its final velocity in the x direction. Now we work out its final velocity in the y direction. Its initial velocity in the y direction plus its acceleration in the y direction times the time. Initial velocity in the y direction is 1 plus the final is negative 0.3. The final acceleration, the initial acceleration in the y direction, and it takes 25 seconds, so we have negative 6.5. So we have negative 6.5 meters per second as the final, negative 6.5 meters per second as the final velocity in the y direction. Okay, now using those two values we can actually calculate the angle at which this direction is moving, at the angle at which this fish is moving. It's a fish, yes. So it's will then be the tangent of its velocity in the y direction, negative 6.50, over its velocity in the x direction, 24.0. That will give me an answer of negative 15.2 degrees. Okay, now since we don't measure from, we measure from the positive x-axis, okay, we just subtract that theta from 360 minus 15.2 gives us an answer of 344.8 degrees. And if you look here, that is the exact answer that you should have gotten, 344.8 or negative 15.2 degrees. So we are correct so far. Are there any questions regarding this particular problem? Any questions at all? If you have any questions, please let me know. I can note down. Now we are doing the last question for today. This is question number 5. This is a conceptual question. Let me see. Go to question number 5. There we have it. If you have any questions regarding question number 4, please let me know so I can address it right now. Otherwise, I assume everyone is with me so far. This is question number 5. question reads as follows. A firefighter, a distance d from a burning building, okay, directs a stream of water from a fire hose at an angle ui above the horizontal, as shown in figure 4.2. Okay. If the initial speed of the stream is v initial, at what height h does the water strike the building? So at what height does the water strike the building? Okay, so let's try and sketch what is happening here. So we have a firefighter. Okay, I'm not going to draw. Well, I can't actually draw. This firefighter is a distance d from a building. Okay, there's a building. He is a distance d from the building. The firefighter is a distance d from the building and directs a stream of water from a fire hose at an angle u. Okay, so he directs water at an angle, give you as ui. Okay, above the horizontal. If the initial speed of the stream is v, so the initial speed of the stream is vi. Okay, so there we have it. So the horizontal component of the displacement, so we have d okay. Let me just see if I can find the actual picture. I might be, if I am drawing the correct picture here. Make it at least an accurate picture of what is happening so you guys can picture it. Okay, they say it's figure 4.21. Let's see. Apologies for that. Four 4.21. I found the actual picture. Okay. So I more or less drew it accurately. Well, in concept, not in artistry. Okay, we have the problem. Okay, they want us to find the question asked, find the initial stream. At what height does the water strike the building? So at what height, work out h. At what height does the water strike the building? Okay, let's see. Okay, so here we have this whole situation. Okay, we can call this theta. Let's call it theta initial. Okay, so the horizontal component of the displacement Let me see. Everyone's still with me? Okay, no questions. Let me check. So we have the problem. Okay. All right. Now that we have the drawing, let me just check something else. The horizontal component of the displacement. Okay, the horizontal component of the displacement is going to be xf. So the horizontal component of the displacement, xf, is equal to vx. It's the horizontal component of the velocity, which is given there in the drawing as vi. So the horizontal component of that velocity times time. That's the distance, the horizontal component of the distance. Now, if you work it out, vxi, the horizontal component, that vxi is equal to the horizontal component of the velocity is just the initial velocity times the cos of theta, and that's theta initially times the time. So there we have the horizontal component of the displacement, the horizontal component of the displacement. So first we work out the horizontal component of the displacement. So we have the horizontal component of the displacement. Thus, the time required to reach the building, which is a distance d away, the time required to reach the building, which is a distance d away, is just thus equal to t is equal to the distance divided by the velocity, okay, which we just worked out to be vi cos theta. Okay, so vi cos theta, which is the horizontal component of the velocity vi, okay, and d is the distance to the building. So now we have the time it will take for this stream of water to reach the building. So at that time, the altitude of the water is, at this time, the altitude of the water is the altitude of the water like here you just work, it's like basic breaking it up into components, and you just work with the symbols. Remember, they tell us the horizontal component of the displacement. The displacement of the water is just the velocity of the water in the x direction multiplied by the time it will take. Okay, now, so the displacement in the x direction is just the x component of the velocity multiplied by the time. Okay, now that time is exactly equal to the distance it must travel divided by its velocity, which you just determined was vi cos theta. Okay, so now we have the distance it travels in the horizontal direction, and we have the time it would take to travel the distance. And at that time, the altitude of the water is equal to, remember we've seen this formula before, yf, which is the height or the distance in the h in the vertical direction, times the velocity in the vertical direction, times the time, plus a half times the acceleration in the vertical direction times the time squared. Okay, now the velocity, the initial velocity in the y direction is vi sine theta, okay, multiplied by the time we just determined is d over v I cos theta, we just determined that, plus, sorry, vi sine theta, which is the velocity in the y direction. It's the just the vertical component of the velocity times the time, which we just determined here, plus a half times the acceleration, which is g 9,8, and of course the time is still d over vi cos theta, and that thing is squared. Okay, that leaves us, if you simplify it, okay, some simplifying it, that yf is, you can just replace as yf is equal to h is equal to yf, so therefore h is equal to, simplifying all of that gives you d tangent of theta, because sin over cos is tangent, that's d, v's cancel, sin over cos is tangent, so it's d tangent theta. Oh, by the way, this is minus g, so that will be negative g over 2, that's d squared cos squared v squared cos squared. Okay, so vi squared cos squared theta. And there you have it. That's the height at which this water will hit the building. Okay, using your equations of motion. Okay, if there are no questions, then I will say goodbye for this week, and join in tomorrow with Arnold and I think James or Arnold, either one, can't remember which. But please try to follow as far as we can and ask questions. None of you asked questions. I've only had one question today. Now I don't know if people were following my work, or was it easy, or and you understood everything, or were you too afraid to ask questions? Either way, you can go back and review all the video in its entirety, and you will see that I then just try to follow my mathematics. Okay, have a great evening further, and I will see you next week. All the best. Bye bye.